Today we're going to talk about polarity in compounds. We're going to start with the polarity of bonds. So there's two different main types of bonds, either polar covalent bonds, where electrons are unequally shared. So in covalent bonding, we have two atoms that are bound together. One of them can have a higher electronegativity than the other one, and the one with the higher electronegativity tends to hoard those electrons. So for this, the electronegativity difference is between 0.3 and 1.7. Sometimes it can go a little higher, but generally if it's much higher than a 1.7 difference of electronegativity, we actually are starting to get into ionic bonding, not covalent bonding. There's also nonpolar covalent bonds where electrons are shared equally or very nearly equally. These are electronegativity differences of between 0 and 0.3. So here is a chart of electronegativities. You'll notice that fluorine in the upper right-hand side has an electronegativity of 4.0. So fluorine is the most electronegative element on the periodic table. The most electronegative elements are fluorine, oxygen, and nitrogen, and chlorine. Everything else has a lower electronegativity than those. You'll notice that helium, neon, argon, krypton have no real electronegativity because they're happy. They don't really want to attract extra electrons. That doesn't make them more stable in any way. Xenon does because it can actually undergo some bonding. So polar bonds. So are these bonds polar or non-polar? So we're looking at the difference between the electronegativity. So chlorine, fluorine. Chlorine has an electronegativity of 2.5. Fluorine has an electronegativity of 4.0, which is a difference of 1.5, which is definitely polar because we're into that polar difference between 0.3 and 1.7. Carbon-carbon bond. So both carbons are 2.5, which means they have a difference of 0. Anything bonded to itself is going to be a non-polar bond. Fluorine-chlorine. So fluorine 4.0, chlorine 3.0, that's a difference of 1, definitely a polar bond. Boron-boron, again something bonded to itself, which means it's going to be non-polar. Boron-hydrogen. Boron is 2.0, hydrogen on the top left is 2.1, that's a difference of 0.1. This is going to be considered a non-polar bond. Carbon-hydrogen. Carbon 2.5, hydrogen 2.1, it's a difference of 0.4. It is polar, but only very slightly polar. So molecule polarity. So to determine if a molecule is polar, you have to look at the polar bonds and determine if it has polar bonds, which most things do. Then you have to look at the symmetry or asymmetry. Is it symmetric in 3 dimensions, not just on paper in 2 dimensions? So we're going to determine the molecules are determined to be polar based on their bond polarity and their geometry. So for water, when you draw it, you can draw it like this. You could also draw it so it looks symmetric in 2 dimensions. But the thing to know, so from VSEPR, valence shell electron pair repulsion theory, you know that this has 4 groups. It's going to form a tetrahedral electron geometry and a bent molecule geometry. It's going to look like this, which means that we have a negative region where the oxygen is and a positive region where the hydrogens are. So hydrogen 2.1 electronegativity, oxygen 3.5, and so you're going to definitely get a polar molecule here. You're going to have a negative end and a positive end. What about CH4, methane? So when we draw it, it looks symmetric on 2 dimensions, but we have to think about the 3-dimensional shape. The 3-dimensional shape, however, is also symmetric. You'll notice that although the carbon-hydrogen bond is slightly polar, they're all poling in opposite and equal directions, which means we're going to have a non-polar molecule. What about carbon tetrachloride? So carbon tetrachloride, this is its Lewis structure. This is its 3-dimensional shape. It's 3-dimensional shape. Again, each of those is pulling in equal and opposite directions. The carbon-chlorine bond is a very polar bond. However, this molecule is non-polar because of that equal and opposite pull of electrons by those 4 chlorines. What about carbon dioxide, CO2? So drawn in 2 dimensions with the Lewis structure. We then have to translate this to 3 dimensions, and it's a linear structure, which means those oxygens are pulling in opposite directions, which means, again, we have a nonpolar bond, a nonpolar molecule. Polar bonds, nonpolar molecule. CH3Cl. That's the wrong Lewis structure. That's for CCl3H, or CHCl3, which is what we have here. This is chloroform. Chloroform is going to be polar because those 3 chlorines are going to pull in the opposite direction from that hydrogen. They have a stronger pull of electrons, so we end up with a positive end where the hydrogen is and negative end where the chlorines are. Our last one is methylene chloride or dichloromethane. This is going to be polar as well. You can draw it in what looks like a symmetric way on paper, but when you look at the 3 dimensions, you get a positive side with the 2 hydrogens and a negative side with the 2 chlorines.